Okay, so sorry, wrong button. That looks promising. Okay, so we're back here. Let me address the issue about the wall first, because let's say this is a new one, it looks pretty clean. Okay, your wall is in this line, line G. Ooh, line G, this line, and then this line. Okay, out of H. And keep in mind that your main columns are in G. Okay, this one will go straight down to the foundation. This one is from the roof, which sits on your main beam. And then the main one that will go to the foundation is this one. So looking at this, you have the floor, you have the walls throughout this, okay? And then perhaps that. And then that. If you want to know how high your wall is, you just need to look at the cross section here, okay? That's a pretty high wall, if you ask me. That's roughly 13.5 meters, even though this is up to that. So let's say it's okay, 13.5 meters. You know, for your information, generally you cannot build the wall straight away with this height. It's gonna crack. Generally, you should add the secondary beams, the, I don't know what it's called in English, maybe just a slip of the tongue. But you need to break the wall. You need to have a sub columns and then sub beams in the walls. But that's a technical issue. Generally, it doesn't concern how you calculate the weight of the wall because it's included, but that's how high the wall is. And then it sits on these lines. So you can calculate the weight of the wall by using that height. And I don't remember if we say half brick wall last time. I believe it is. So half brick wall is 180 kilogram per square meter. But it's a wall, so the area is, you know, in the vertical direction. You can turn this load into the uniform load acting on your beam by multiplying with the height. And the height you already know it's 13.5 meters. And now you have the uniform load that comes from the wall acting throughout these red lines. So to sum the load of the wall onto your column, you may say, okay, again, using the tributary width of sort, let's say this is the length of the wall that is responsible by this column, okay? And let's say the wall on this side is of course onto this one. And that should be on that one. Oops, sorry. And then this one, this entire wall should be on this one, okay? And now you have a bit of a difficulty because for this wall, if you say it's not directly on the column line. So if we are going to be super accurate about it, you may want to sum the load of the wall and then act on the beam and then, you know, do whatever you want to. But I would say, because it's so close to this column, you can say this wall, this part is taken care of by this column right away. There's no need to do anything else. Okay? So does that answer the question about how you should take care of the wall? Is the wall done? Okay. Okay, cheers. I'm glad you asked, and I'm glad that I can give the answer so that you guys can proceed to do things very correctly in a way. Okay, so that's the wall, and I was going to draw something about this system. So let me go to where we stop in here. Okay, and then I'll go back to that again. Okay, to explain the red line here. So, okay, I was here, right? So from this picture, you can see that if you consider this column, the load that acts on it is the load that coming from the roof, correct? And then when you consider the lower portion of this column, of course, it has to take the load from the second floor plus the roof, okay? So the load from the roof should not go anywhere. And yes, of course, it makes sense that this column will carry more load because it's lower, okay, before it goes down to foundation. But on the first floor, if there is going to be some kind of structure, that's going to be concrete structure. So that doesn't concern us. But keep in mind that when you want to design the foundation, you have to include the weight of the first floor as well. Well, that depends on how you are going to construct the first floor, because sometimes they would use the structure that called the slab on ground or ground slab. So whenever you see that one, it means that the slab sits on the ground because they don't want to put the load of the ground floor onto the foundation to reduce the cost of the piling system and so and so. So doing that, I'm talking about the ground floor. It doesn't have anything to do with us, but I think you guys should know. So you have the freedom to choose the ground floor not to sit on the structure, just to sit directly on the soil, or have the ground floor sit on structure. You may be able to do this outside Bangkok where the soil is pretty strong and it has good bearing capacity. But if you do it Bangkok, the ground floor will sink very rapidly. Not a very good idea. And like I say, if you put the ground floor on the system, on the structural system, it means that your foundation will have one more floor to carry. It's going to cost more in terms of pile and everything. But the good side is that you have the system that will go together. So the ground floor will not have problem with the settlement or anything. It will sit solidly on your structure. Okay, but you don't have to do that always. Sometimes if you have a very capable soil that has a good bearing capacity, you may choose to have the ground floor on the soil as well. So many construction outside Bangkok do that to save some money. But it also depends on how much the load the ground floor has to carry as well. Let's say you're building a factory or warehouse, even though outside Bangkok, and your warehouse will have to carry a lot of load. So it may not be a good idea to put the ground floor on the ground or on the soil because of the heavy load. Okay, and this is the general case that you should know when, let's say, in your house, the garage, generally people would try to save money by not putting the garage on the structure of the house to reduce the weight of the foundation. So if you do that, your garage will crack because the floor of the garage will sink so rapidly because of the soil condition in Bangkok. And because you guys didn't go out with me in structural analysis number 1, but I can tell you that if you walk around Wissawa Watana building, you see cracks appearing, along the stairs, right? The approaching stairs that you guys walk up to the building. That's because the ground around the building itself, the walkway it's not on the structure. So they sink more rapidly. But the stairs are, part of the stairs that are on the structure will not sink so rapidly. And you will see the crack right away when you have two structural systems attached to each other. The one on the structure will not sink. It will sink, but in a very slow rate. But the ones that not on the structure will just go freely, causing the cracks to appear between the two connecting areas. All right, so let's come back here. Now you see what you guys are up to. You know, when you sum the load on the column, you need to draw what I call the column load diagram. Because when I let's say when I give you the exam, I'm going to give you the information like this. So this becomes a column, and you will have the load coming from the roof that this column will carry, right? And then for this part of the column, this is this. Then this is this. This will have the additional load. Excuse me, I should erase this one. It look appropriate. Okay. All right. This column will carry the load coming from the roof, and then therefore this column will carry the load coming from that. So whenever you do the design, you should always have the table to show the load summation. Okay, which floor you have how much load. All right, and then when you design it, it becomes clear to you that okay, this column will have to carry the load from the roof, and then when you're designing this column, it will have to carry the load from here and then from there. Okay, that is called the column load diagram. Okay, is there any question on this? We may move on to take care of the second floor. I will repeat that again. No question? Good. So again, the column here is unfortunately a bit complicated because you have the column coming in from the roof, which sits here, and then it doesn't go down directly to the foundation. So it changes the location. Well, that happens, you know, because of the demand of the roof is not the same as the demand of the area down there. So you see, because they need to do this because I don't. You should look at this. Okay, there you have the need for the space of the car to come in to load whatever that is that you need to put on, and then this is the office, and then the approaching area. So it's only natural that, you know, because of the requirement like this, you guys need to change the location of the columns. Okay, so don't complain. It's a simple job for the engineers to do it. So all right, because of this, I sort of want you to experience the good approximation. You may want to use the tributary area as well, but I say, you know, you can also do this. So let's say, even though you see that there are many beams in this area, but we are taking care of the column. So you may say, you're gonna use this area. Okay. Again, it is the tributary width, you know, half the distance between this column and that column. So it's half here, and then it's half there. So this becomes the strip between the two main lines that you are, these two columns we have to carry. Correct? If there's no space here, if the area was stretched down to this side, you can use the tributary area, half and half. But in this case, let's try to do this and see what happens, okay? And then if you want to see how accurate this gets, you may want to use the tributary area again to see how different it is between the two cases. And then don't forget the column load from the roof as well, okay? So with this in mind, we go back to this, okay? And that strip will look like this, right? You have the column down there. So this is your second floor. And then I'm going to put that strip on this. Okay. And whatever the width you have here, if you multiply this width B with your load, you will get the uniform load acting on this sort of beam, right? Well, it's not entirely the beam, it's the load that I want to say approximate how much this one will carry and that one will carry. But I want to have a good approximation this time. So I use the tributary width between the columns. So there'll be one more columns here with the same tributary area like this, and then another one down here, right? So we use the area half between them. It's sort of like analyzing a big beam. Okay. So from this becomes the free body diagram that you can analyze, that you can use to analyze the loads on the column. Okay. So this is your W multiplied by B. And then if I am not going to write it at the same time to reduce confusion, you will have the same structure, but this time it's the same thing. Second floor, and then the same line, but this time we focusing only to get the roof load onto the column. Okay, so that is the load coming in from the roof. Again, this time it's just the point load here. So you can just look at this free body diagram and analyze it as a simple beam to get the roof load on your column. So from this, again, I can draw the free body diagram of the analysis there. Okay. If you can see the picture, in fact, you can, do this and that at the same time. Just keep in mind that the floor is stretched to this line. Okay, so that load is now that doesn't stop at the same location as where the roof comes down. So that is your W. And that's how you should get your load on the column, and plus the load from the walls. All right, that's it. So now I think we have time to cover a few more things. So let's say, another request from you to show the how to use the catalog. So let me try to write something. Okay. So let's say I have the floor tiles, the load, floor tiles, let's say 120 kilogram per square meter. Okay. And then I know that the live load that I'm going to use is maybe 400 kilogram per square meter. And then I'll have, say, miscellaneous load. Maybe I would consider the, say, ceiling of the floor underneath. the piping, the internet viaducts, you know, whatever, etc., etc. So I'd say maybe 50 more for me. Okay, so this is what we can say is superimposed load, because this load will be on the floor. It will be superimposed on your floor. So when you can, you know, summarize what load that your floor has to carry, you just sum them up. So that's 570 in total. So this is the load where you should enter the catalog and pick the floor that has the superimposed load capability greater than this number. Okay, so this is the load that you should use this to enter your catalog. How do you spell it? Something like that, right? And then once you have the catalog, you will get the type of floor, right? But when you know the type of floor, you will also know the date load or the weight of the floor itself. Okay, so let's say I know that, again, the weight of the floor is, say, maybe 300 kilogram per square meter. So that means the total load of your system now is going to be the floor 300, the tiles, sometimes I just call it finishing, 120, oops, run out of space, the live load, let's say miscellaneous, here 50, and then the live load of 400. So okay, this is your total date load, and that is your live load that you should put on your beams and your columns and stuff to make sure that your building is safe. All right. Does that answer you? How about the roof load at the left side? You mean the canopy? Good spot. The canopy that I am asking you to design, right? Yeah, you should add that to the column as well. Yeah. So let's go back to that. So, you know, I like that. This is a common sense thing to do, right? You always yourself, not always, you imagine yourself as an engineer. And let's say you have this stuff here. You mean this, right? That? Of course. What would carry it, folks? What would carry it? Your columns, right? So should you add that to your calculation? What do you think? Yes, right? That is a yes. So I was going to talk about that. Let me see if, what about this? I don't think it should concern you, because we don't focus on that. Okay, that's fine. It's a small stuff. So yeah, it's fine. Let's forget about the stairs for the time being. So when we talk about that, the canopy, say that's your column, right? Then you have the canopy coming out like that. Oh, I'm trying to draw. Difficult. Okay. Here. Then you have the canopy coming out. The canopy here, just the entire canopy has to be supported by this column, right? This column, oh, sorry. This column will support the canopy, no doubt about that. And therefore you should add the load for the entire canopy to the column. Okay, but I think first of all, it's rather small. And what did I say the last time? This is like 6 meters, right? And then another column down there, and then you have half the width as your tributary width. And then another half here. So meaning one column will take one canopy. And if I draw because we don't have this on our drawing, we don't have the plan for the canopy. So, but I guess you guys can come up with it, right? So this is the plan for the canopy. Let me go back and try to look at this very quickly. So it's every 5 meters, right? And the canopy, the last time we say it's 6 meters. So you're gonna have something that looks like this. I bet the column should be that way. So this is like 5 meters. And somehow 5 is longer than 6. Well, let me fix that. You know, whenever you can, you should always draw the proper size of the things, the good proportion. So this is like 6 meters long for the canopy. So that means the weight of this canopy area that should be on one column is this. Because we have column on one side, right? So the entire load of the canopy should sit on one column per one tributary area. So that is also 5 meters. Okay, but you know, this is a canopy just to give you a shade. So the material itself should be light. Think about plastic roof or polyester roof. I don't know how it's called, maybe polyester. And then the light purlin. And the live load should not be more than, you know, typical roof. I'm not going to tell you. You should be able to find that yourself. And then the weight of the polyester, which is pretty light. Okay. And now let's look at the roof again. Say I'm telling you to put the purlin at the every 1.2 meters, right? And one purlin, therefore, you can look at it as a simple beam. Uh, 5 meters long with the tributary width of just 1.2 meters. Okay, so that's the uniform load acting on the purlin. And when you can calculate this simple reaction, it's this one. Okay, that's the reactions from purlin. Okay, so you should know that one canopy truss would have to take 2 reactions, right? Because you have another purlin coming in. So basically it's just the tributary area multiplied by the load. Okay, and that's how you can put the load on your truss. So need to calculate anything yet, okay? Just get the right load. All right? That's pretty much I want to cover today. Any question, folks? Folks? Okay. No speaking. Just we need to calculate two parts. We have two live load. Yes, that's correct. That is correct. You have two areas with two different live loads. But it's the same territory area, you know. You can recalculate very easily by, you know, using the ratio. Correct, because it's linear. It's linear. And this building is tiny. But you know, the challenge of doing the steel structure is that you need to get the equilibrium correct. Just let's say if you mess up the frame, there's nothing to hold on to. It's just, everything just gonna go. You know, I was thinking about taking a photo and show to you in the class today, then I forgot because of the traffic jam. They just erected the huge steel buildings around my kids' school. But then I look at the truss and wow, they use such big members, you know. The members are so big that I think it feels crazy. But I don't know. Sometimes when I can tell you this, if you do things right and you look from the size of your structure from afar, you will feel that, yeah, it looks good because it doesn't look too big, it doesn't look too small. If it looks too big, it looks ugly, it looks thick. If it looks too small, you feel like it's probably not safe, it's gonna wobble a little bit maybe. So when you do things correctly and you look at the size of the structure that you construct, it looks kind of makes sense. Everything makes sense. I remember, you know, long time ago, I was standing and looking at my own structure. I thought it was big on paper, you know, and then I look at the real structure and wow, it looks proportionate. It looks like everything makes sense. But that, you know, the beam, the span length was 12 meters. I use only no more than 50 centimeter deep steel beams and 12 meters long, but with the depth only 50 centimeters. Some would go crazy and think, oh, that's too small, I need to increase. But when I look at it from the real side, it looks, wow, okay. You know, but then I look at the truss this morning and say, wow, it look big, especially the webs. So when you look at things like that and say, wow, it doesn't feel right. Maybe it means that they over design a little bit. But I was going to say this: when you see things that probably, you know, you can make a reason out of it, there may be some non-engineering reasons involved, such as, well, they got a lot of that kind of section in stock and they want to use it. They don't want to buy the new section, so they just don't care. They're just going to use it. And that's why they probably can have big sections. But that kind of reason is not engineering. All right. So, is there any other question?
Teacher.
Yep.
For the second floor, the load that come from the extended column from the roof.
Extended column from the roof.
Yes, the column that doesn't go down on the foundation.
Okay. That blue one.
On the left hand side.
Oh, you mean this? This?
Yes, it should be the point load on the beam, right? And
Yes. It should be the point load on the beam, and then the beam is attached to the column. So everything goes into the column eventually.
the nearest one, right? Just
Yes.
only the nearest one.
Yes.
Okay.
Because
Okay.
go on.
We don't need to calculate it as a continuous beam, right?
No, because the way you construct the steel structure is this. Let me wow, that's a good question. Say the column will come straight down like this. Okay. How I should draw this. And then this beam will come in and be attached to the side of the column. It's not like concrete where you can just run through the column. Right? Can I erase this portion now? Oh, I can. Okay, looks beautiful now. So this, so your roof comes down on this column, on this beam. And then this beam is attached to this column on the flange side, perhaps, or on the web. It doesn't matter. So that's a column. Okay. And then your beam will be attached to this column by ways of moment connection. So that's how it can stay here like it is. So the free body diagram looks just like that. Okay, that's your column, and therefore you can write the beam as simple as this.
Okay, thank you.
Yeah, which in terms of the load, it's pretty much like, say, you having this thing. It's the same, except but for this, you probably have the say the seesaw effect on the next one. But let's say we don't consider this, and because in the real thing, it's like this. Good spot. I don't like it when I feel like my drawing is crooked, you know. Let me fix it. Okay, better. All right. Roof. Okay, any other questions? Good question, this. So, you know, let's check. You may want to calculate the load from this column separately. You may notice that they use the same column number. So, you know, it's part of the art of design, you know, because let's say generally when you look at this, see, it's the same column number here with this. So in the end, after you investigate the load, you may decide later that I'm going to use the same size, because they're not going to be exactly the same, but they may be so close that you can use the same details. All right. So part of the job as a designer is to investigate the load and try to group your columns and your beams into a very orderly fashion, so that, you know, the integrity of the building is nice as well. You have the nice group of columns. It's good to be very thorough when you investigate the load and everything, but you don't go crazy and change the detail every time the load is different. Right? For example, you may sum the load, and here is 98 tons, and this is 1.2. So maybe the same size can be used together, you know, stuff like that. It's art. So there is no specific answer to this. So investigate the load first. It's like this, and then we'll talk about the load on the beam later and how you can group the beams. And this is when you see the load on the columns, it's you can group the load on the you can group the columns. What kind of section you should use? Should you use the same? Should you use it differently? Okay. Okay. Is there any other question? Good question, Dan. And I'm glad that this is recorded. This is being recorded as well. No? So, no question? Okay. I'm gonna stop the share and I'll go back to main screen. I'm gonna stop the record so that the file doesn't get too unnecessarily big. Okay.